Hey, welcome to The Explainer. Today we're going way beyond just simple, straight lines. We're going to build a whole new toolkit for describing how things move on any flat surface. You know, like the graceful arc of a thrown ball or a planet swinging through space. Let's get right into it.
So think about it. A planet, a pendulum, a Ferris wheel, they seem totally different, right? But what's fascinating is that in the world of physics, they all speak the exact same language. And by the time we're done here, you're not just going to understand that language, you're going to start seeing it absolutely everywhere.
All right, so to get there, we've got to build up our vocabulary first. We're going to lay down the essential concepts that let physicists talk precisely about where something is and how it's moving. Not just forwards and back, but anywhere in two dimensions.
You know, for something like temperature, a single number is all you need. But for motion, it's not enough. That's where vectors come in. Think of a vector like a perfect instruction on a treasure map. Walk 20 paces northeast. It has a size, or what we call magnitude, the 20 paces, and it has a direction, northeast. That whole package deal is a vector, and it is the absolute foundation for everything we're about to do.
And this is where things get really clever. A single diagonal movement can actually be pretty messy to work with. So the brilliant trick that physics uses is to split that one complicated movement into two much simpler ones that are at right angles to each other. Here's exactly how it works. Picture our vector as an arrow drawn on a grid. Now, if you shine a bright light straight down from above, the shadow it casts on the floor, the horizontal x-axis, that's your left-right part. Then shine a light from the side, and its shadow on the wall, the vertical y-axis, is your up-down part. All of a sudden, this complex diagonal problem just became a super simple how much over and how much up puzzle. It's a total game changer. Okay, and this leads us to a super important distinction that can trip people up. Let's say you wander all over a park for an hour, but you end up right back where you started. The distance you traveled could be huge, maybe a couple of miles, but your displacement, which is the straight line arrow from your start point to your finish point, is zero. You're back where you began. Physics is often way more interested in that displacement vector, the most efficient path from A to B. So we can describe where an object is. Great. But in the real world, things rarely just sit still. The next logical step is to figure out how to describe how that position changes as time goes by. This is so important. In everyday conversation, we use speed and velocity like they're the same thing. In physics, they are not. Your car's speedometer, that tells you your speed. It's just a number. But your velocity is a vector. It's 60 miles per hour heading north. So get this, if you change your speed or you just turn the steering wheel, you have officially changed your velocity vector. Just let that sink in for a second. We tend to think of acceleration as hitting the gas or slamming on the brakes. But based on what we just said about velocity, is it possible to be accelerating even if your speed is perfectly, totally constant? And the answer is a huge yes. Think about a race car going around a circular track. It's holding a steady 100 miles per hour. The speedometer needle doesn't move. But its direction? It's changing every single split second. And since its velocity vector is changing, that means it is accelerating. Something has to be causing that change. So here's the big takeaway. In physics, acceleration is way broader than just speeding up or slowing down. It is any change in your state of motion. Turning is a form of acceleration. I'll say that again. Turning is acceleration. And once you really grasp that, you've unlocked the physics of curves and circles and so much more. And speaking of circles, let's take our new language and apply it to one of the most perfect patterns in nature, circular motion. This is where all these ideas really start to come alive. First up, let's get the rhythm down. The period is just the time it takes to go around once. Let's say 2 seconds for a full lap. The frequency is the flip side of that coin. How many laps do you do in 1 second? Well, in our example, that would be half a lap per second, or 0.5 hertz. They're just two different ways of talking about the very same pace. Now, you're probably used to measuring angles in degrees, right? 360 degrees in a circle. But for this kind of stuff, physicists use a much more natural unit called the radian. And it's actually a beautiful idea. Imagine you have a pizza. If you take the length of the radius from the center to the edge, and you curve that same length along the crust, the angle of the slice you just made is exactly 1 radian. It's a unit that's born from the circle itself.
So, just like regular velocity tells you how fast you're covering distance, angular velocity tells you how fast you're sweeping through an angle. It's how quickly something is spinning or orbiting, and we measure it in, you guessed it, radians per second.
And here is where it all clicks together. That object moving in a circle at a perfectly constant speed, it is constantly accelerating. Why? Because its direction is constantly changing. And where is that acceleration pointing? It's always pointed inward, right toward the center of the circle. That's centripetal acceleration. It's the constant inward pull that keeps the object from flying off in a straight line. And check this out. The formula that governs it is so simple and elegant. The centripetal acceleration, A, really just depends on 2 things. How fast you're going, that's V, and how tight the circle is, that's the radius, R. It tells you that the faster you go, or the tighter the turn you try to make, the more acceleration you're going to need to pull it off.
Okay, for our final piece of the puzzle, we're going to uncover one of the most beautiful and honestly surprising connections in all of physics. We are about to see how the perfect, smooth motion of a circle is secretly hiding inside the simple back-and-forth rhythm of things that wobble or oscillate. I want you to really picture this. Just imagine a single glowing dot, spinning smoothly around and around and around on a big, dark wall. We totally get this motion now, right? It's got a constant speed, a period, a frequency, and, as we just saw, a constant acceleration pointing to the center. Now here comes the magic. Imagine we take a flashlight and shine it from the side of the room, so we cast the dot's shadow onto the wall behind it. Well, that shadow can't go in a circle. All it can do is move vertically. It glides up to a peak, slows to a perfect stop, then reverses and glides all the way down. It's just a simple, repeating back-and-forth rhythm. This little back-and-forth dance of the shadow, it has a name, simple harmonic motion. This is the exact motion of a swinging pendulum, a mass bouncing on a spring, or a vibrating guitar string. And now we see its secret origin story. What looks like a simple oscillation is really just a one-dimensional projection. It's literally the shadow of perfect circular motion.
And what's so cool is that the language we used for circles maps perfectly onto this new motion. The shadow's maximum reach from the middle, its amplitude, is just the radius of the original circle. The time it takes for one full back-and-forth swing, its period, is exactly the same as the circle's period. And its fundamental rhythm, or what we call pulsation, is taken directly from the circle's angular velocity. It all lines up.
So let's just quickly recap our whole journey. We started with vectors, because you need both size and direction to talk about 2D motion. Then, we redefined acceleration to include any change in velocity, even just turning, which was the key to unlocking circles. And finally, we saw that the simple back and forth of harmonic motion is beautifully and forever tied to the smooth spin of a circle. And this really brings us to the final thought. From the tiny vibrations of atoms that make up everything, to the light waves hitting your eye right now, to the majestic orbits of the planets, this deep, deep connection between rotation and oscillation echoes all throughout the cosmos. So the question to leave you with is, now that you know what to look for, where are you going to see this pattern next?